In today's lecture, we will start our discussion on on-rotor three-phase induction motor. Let's get started. As we saw in the last lecture, for squirrel cage type rotor, we used metallic bar as conducting terminal in the rotor side. As name suggests, in on-rotor case, in the rotor side, we will have windings, copper windings, instead of using bars. For squirrel cage case, both the sides of the copper bars were shorted. In on-rotor case, we'll not make one side shorted. Instead, we'll keep it open to connect external resistance with the rotor. What is the benefit of connecting external resistance in the rotor side? We will discuss it later. For the time being, let's see the construction. This is the rotor construction. There will be windings in the rotor side. These are copper windings. These windings are to be made in a such a way so that we'll have star connection, three-phase star connection in this way, or Y connection. Sometimes we call it Y connection. And we know, if we consider this is an equivalent circuit of the squirrel cage rotor, by default the other sides are shorted because for squirrel cage both sides of the bars are connected with end rings, so they are shorted by default. However, for one rotor case, these three sides are not shorted automatically, rather they are connected with slip rings, three slip rings. Here we have slip ring 1, slip ring 2, and finally slip ring 3. First one is connected with slip ring 1, second one is connected with slip ring 2, and third one is connected with slip ring 3. And from these three slip rings, three connections are taken out using a brush. If these three sides are shorted, there is no difference in the equivalent circuit with the squirrel cage case. However, there is a provision of adding three resistances here, and these are variable resistance, and we can make other side shorted. Now here we need to understand that this resistance is the internal resistance for each phase configuration. So this is R1, this is in inductive reactance XL1, and it will also have R1 value, XL1 value, as they are having balanced load. This is R1, XL1, and this is the resistance connected externally, that is R2, 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 and this resistance is connected with each phase. So for phase 1, the total resistance will be R1 plus R2. For phase 2, total resistance will be R1 plus R2, and similarly for phase 3. Oh, here I made a mistake. This will be XL1 and this will be R1. So from here, three connections will be taken from the windings, and there will be three slip rings, and we can connect external resistance using these slip rings. like this configuration. If we do not connect external resistance, we need to make the other side short. Then the working principle of this on-rotor case is similar to that of our squirrel cage case. Whenever there will be a rotating magnetic field around this rotor, the rotating magnetic field will cut these windings, and when there is a cutting of magnetic field, EMF will be induced as this side is shorted or shorted through external resistance. Whatever the case is, the current will be flowing. When there is a current flowing through these windings, that current will produce a force. Eventually, that will produce a torque, and the rotor will start rotating. So, if we name it, we can say these are windings. These three earths slip rings. Definitely, there will be two bearings. This is one bearing. There should be another bearing. This is bearing for holding this rotor, and the equivalent circuit of this winding can be portrayed in this format, where R1 is the internal resistance of the windings and XL1 is the inductive reactance of this winding for each phase. One side of each phase is shorted to make it Y connected configuration, and the other side is shorted through slip rings. We can either make other side shorted, or we can connect external resistance whenever it is necessary. I repeat, what is the use of this external resistance? We will describe it later. For the time being, we know we can connect external resistance for on rotor case. Remember one thing, it is not possible to connect external resistance with the squirrel cage configuration, because once the squirrel cage configuration is constructed, we cannot change the construction, because squirrel cage structures are made by molding aluminum or copper. These are the typical figures of squirrel cage rotor and on rotor. We can see in a squirrel cage rotor we have metallic bar current connected from one side to another side, and in on rotor we have windings. The one side of the windings are shorted like this one, and another side is taken out and is connected with these slip rings, and from the slip rings, using the brush, we can connect external resistance like this configuration, or we can make other side shorted. Now suppose we have a stator configuration with two pole systems like this. This is the side view of the stator. This is fed by three-phase supply. Three-phase currents are going inside. I'm not drawing the internal diagram again, because we know what is the internal diagram. Whenever we'll give this three-phase supply, there will be a creation of rotating magnetic field. And suppose a rotor is placed inside this hollow part. So we have bars, and whenever we'll give this three-phase supply, there will be a creation of rotating magnetic field. This side is north, this side is south. It will start rotating in one of the directions. For example, it is rotating anti-clockwise direction. Then the speed of this rotating magnetic field will be synchronous speed and can be defined as ns equal to 120 f e over p, where f is the supply frequency and p is the number of poles per phase. So when this rotating magnetic field starts rotating, this field will cut this bar and there will be a creation of EMF. For example, at standstill, that means rotor is stopped, but we have given the supply. At that moment, what will be the current frequency that is flowing through this bar? At one moment, this north side will be there. Then after some time, the south pole will come here. So for magnetic field cutting due to North Pole will produce a current in one direction, and magnetic field cutting when it comes here due to South Pole will produce an opposite current than the previous one. So there will be a creation of alternating current. Now what is the current frequency that is flowing through this metallic bar? When the rotor is at standstill and this magnet is rotating with this synchronous speed, which is synchronous by this supply frequency, so the current produced here will have exactly same frequency of the supply frequency. However, when the rotor starts rotating, if the rotor rotates with the speed of synchronous speed, though it is not practically possible, but if the rotor starts rotating with the speed of synchronous speed, the rotating magnetic field is rotating in this direction, anticlockwise direction with ns speed, and rotor is also rotating in the anticlockwise direction with ns speed. So the speed difference between them will be zero. So there will be no magnetic field cutting. And as there is no magnetic field cutting, there will be no induced EMF in the rotor side and no current will be flowing, and the frequency of that current will be zero because the relative speed is zero. So the frequency of the secondary current, that means the current through this rotor side, depends on the relative speed between the rotor and the rotating magnetic field. Now let us consider the speed of the rotor is nr and the current flowing through this rotor bar is having frequency f2. So if we apply this equation, then current flowing through this rotor bar will have the equation in this format: F2 equal to P into, instead of writing ns, here we need to take the speed difference between the rotating magnetic field and the rotor, ns minus nr divided by 120. Now if we multiply ns minus both in numerator and denominator, we'll get this. Now let us separate this portion so that we can write in this format: F2, which is the frequency of the rotor current, equal to P into Ns divided by 120 into Ns minus Nr divided by Ns. We know Ns minus Nr divided by Ns equal to slip, is slip, and Pns over 120 equal to Fe, where F is the supply current frequency. Fe is the supply current frequency and S is the slip. Rotor frequency F2 equal to S into Fe, where F is the supply frequency, S is the slip. And this is natural. When rotor is at a standstill, what will be the value of S? Rotor is at a standstill means NR equal to 0. That means rotor speed equal to 0. At that moment, the rotor frequency, rotor current frequency will be exactly equal to the supply frequency. When S equal to 1, F2 is equal to Fe, which means rotor current frequency is exactly equal to supply frequency. But when rotor starts rotating, the current frequency through this rotor bar depends on the relative speed. So when the relative speed will be higher, then the frequency will also be higher. When the relative speed becomes low, then the frequency of the rotor current becomes low. When relative speed becomes 0, at that moment nr equal to ns, which is not possible for motor case, then F2, that means rotor current frequency becomes 0. Actually, as there is no magnetic field cutting, no current will be flowing. There will be no question of current frequency. So frequency can be written as 0. Frequency of the rotor current can be written as 0. So the title can be written as rotor current frequency. The basic theme in nutshell is that the rotor current frequency depends on the speed of the rotor. If the speed of the rotor is zero, then the relative speed between this rotating magnetic field and the rotor will be the highest for motor case. Here it's better to write rotor current frequency. Next we will discuss on the loading of a motor. Loading of an induction motor. Definitely it will be three-phase induction motor because we are discussing three-phase induction motor, but loading of any motor has similar concept. Now what do you understand by loading of an induction motor or loading of a motor? For motor case, loading means we apply a mechanical load to the shaft. That means applying mechanical load to the shaft. If we apply mechanical load to the shaft, that will exert more torque, that is called load torque, on the motor. For induction motor case, if we increase the mechanical load on the shaft, the motor will begin to slow down. So if rotor speed slows down, what will happen? The speed difference between this rotating magnetic field and rotor will be increased. Remember, reducing the rotor speed doesn't mean the speed of the rotating magnetic field is also reduced. The speed of the rotating magnetic field is fixed and it is 120 Fu over P. Unless or until we change the supply frequency, the speed of the rotating magnetic field will not be changed. And generally it is fixed because supply frequency is constant. And once the motor is constructed, the number of poles per phase is also constant. So when we say the motor speed is reduced, it means the speed of the rotor is reduced, not the speed of the rotating magnetic field. So if the speed of the rotor is reduced, then the relative speed between them will be increased. If the relative speed between them is increased, the magnetic field cutting on the rotor bar will also be increased and more induced EMF will be there and more current flowing will be there in the rotor bars. So if we apply mechanical load to the shaft, the rotor speed will be decreased and the motor and the mechanical load will reach a state of equilibrium when the motor torque is exactly equal to the load torque. Motor torque means motor's produced torque. Motor produced torque is exactly equal to the load torque. We'll have lot of discussion on this later on when I'll show you the torque speed characteristics curve. Now for the time being, we need to know if we apply load of an induction motor, the speed of the rotor will be decreased. If the speed of the rotor is decreased, the value of slip will be increased. Because if the value of NR is decreased, NS is constant, so the complete value of slip will be increased. So if the speed of the rotor is decreased, the value of slip will be increased. If the speed of the rotor is increased, the value of slip will be decreased. Just keep this in your mind. This concept will be needed in future. Now if we have a motor like this, suppose this is a motor and inside we have rotor and this is the shaft, these are the supplies. Any load connected with the shaft that hinders the motor to rotate, that is the mechanical load of this motor. Now this load varies with the motor application. For the ceiling fan that we use, that is also a single phase induction motor, and the blades connected with the fan, generally we have three blades 120-degree apart. These three blades are loads. If we run the same induction motor without the blades, the motor runs with higher speed. If we connect three blades, the speed slows down for the same supply. For water pump that we use in our household, the load is the height of the water. If we pump the water with higher height, then the motor will feel higher load. In this way, the load can be defined. So what I meant to say, If we increase the load of any motor, that means increasing the mechanical load, then the speed will be slowed down. And if the speed is slowed down, then the slip value will be increased. Next, we'll discuss on the topic that is voltage induced in the rotor. Induced in the rotor. Remember, it is obvious that whenever there is a rotating magnetic field and the rotor is at a standstill due to cutting of this magnetic field on the rotor bar, definitely there will be induced voltage because this rotor bar is experiencing change in magnetic field. So there will be induced voltage. Now let us consider the induced voltage in the rotor side at standstill is E2 prime. So the induced voltage in the rotor side at standstill. At standstill means the rotor is not rotating, is E2 prime. Now when the rotor is rotating, the induced EMF depends on the relative speed between the rotating magnetic field and the rotor because the cutting depends on the relative speed. If the rotor rotates with the speed of synchronous speed, then there will be no cutting. But if the rotor rotates with a speed difference between them, if the difference becomes low, then the cutting of magnetic field will also be low. In that case, under running condition, the induced EMF will also be low once the rotor gains speed. At standstill, the speed difference is the highest. So that will be the highest induced EMF to the rotor side under the motoring condition. So when the rotor is rotating, the induced EMF depends on the speed difference, and speed difference is defined by a term that is slip. So with a similar pattern that we wrote for frequency case, we can write the induced EMF at the rotor side under running condition. E2 can be written as S into E2 prime, where E2 prime is the induced EMF at standstill. Under running condition means we need to know what is the speed. Whatever the speed, that will give us the corresponding S value, because if we put the value of speed here, we'll get the corresponding S value. And if we multiply that S value with the EMF at standstill, we'll get the EMF under running condition. So this is the induced EMF at the rotor side under running condition. Now we have some beautiful phenomenon. We can measure the speed of the rotor by using tachometer. Once we can measure the speed of any rotor, we can figure out the value of S. Once we know the value of S, if we know the induced EMF or if we know the supply frequency, we'll be able to know what is the current frequency in the rotor side under running condition at that speed. What is the induced EMF in the rotor side under running condition at that speed. We'll continue from here in the next lecture. Thank you.